Okay, in the remainder of the course, we'll be covering sensitivity analysis, perhaps parametric analysis, plus decomposition for large-scale linear programming problems that may have special structure, plus some exposition to network flow problems. I'm not sure to what extent we can go into it. Nevertheless, at least we'll give a shot at it. Let me cover sensitivity analysis today. This is an important topic in any optimization type of problems, not only in linear programming. In fact, sensitivity analysis is also important for design problems as well. You don't have to have any optimization on hand. Nevertheless, it's important. So the main question for these kinds of problems is you solve a given problem using some given data. So the given data defines an instance of the problem. You solve the problem, you have a solution, and you realize later that part of the data is in error, or it's supposed to be changed, or possibly some new information is acquired, which tells you that you should revise your data. So the first thing that comes to mind is to resolve the problem using the new data. But then if the change in the data is small, you may ask yourself, well, can I salvage the old solution? And if the answer is yes, of course, you use the old solution. If the answer is no, can I then move from my old solution to a new solution which accepts or which is admissible relative to the new data? That's the basic question. And we'll look at possible changes in the following parameters. The cost data may change from C to C cap, and the right-hand side may change from, say, B to B cap. A column of the A matrix may change from AJ to, say, AJ cap. You may also have a new activity introduced to the problem, so add a new activity. And you may also add a new constraint to the problem. All right, 1 and 2 are straightforward. Number 3, I'm talking about a change in a column of the A matrix. Now, of course, it is possible that the entire A matrix may change in a more arbitrary way, not only one column at a time, but in a more general way. But if there's too much change in the A matrix, that's too much to handle. Sometimes it's just better to just resolve the problem from scratch in that case, because the left-hand sides are, they change the entire problem structure. Whereas the other ones, they don't really change the entire problem structure to that extent. So the main strategy here is the following. We assume we have a solution to the problem. So what we do is first determine which part of the old optimum tableau is affected by the change. And accordingly, revise the old optimum tableau so that it is consistent with the new data. So revise the old optimum tableau as necessary to make it conform with the new data. And once you make that revision, you may have you may lose your optimality. You may lose your optimality in two different ways. Number one, you may lose primal feasibility. In other words, the right-hand side values, the B bar in the tableau, may turn negative due to a possible change. You may also possibly lose dual feasibility, which refers to the row zero numbers. Okay, for a minimization, your reduced costs are less or equal to 0 at optimum, but some of them may turn positive, in which case, of course, you need to continue with your regular simplex method. Sometimes you may have lost primal feasibility as well as dual feasibility at the same time, which is more complicated, in which case, of course, you have to know what to do in that case. Well, I'll tell you what to do, and we'll see how to handle each one possibly. Okay, so if primal feasibility is lost due to the revision, if only primal feasibility is lost due to the revision, then that means the right-hand side value becomes negative, at least in one component. So in that case, use dual simplex method. If only the dual feasibility is lost due to the revision of the data, which means the reduced cost vector has the wrong sign in at least one component. In that case, of course, use the regular primal simplex method, meaning that you enter one appropriate variable and just continue with the... Okay. If both are lost, then this is complicated. There are many, well, there are a few different ways of attacking this, but the one I suggest is the following. Then multiply by -1 those rows I for which BI turned negative now, okay, BI bar, sorry. The current value turned negative relative to the new data. And then, of course, that multiplication will make your unit vector, or the 1 in that particular row, the basic variable that has a coefficient of 1 in that particular row, it will become negative. Okay, so you're not able to use it any longer. You need a unit vector. So for that reason, you just introduce a unit vector by adding an artificial variable to that particular row. So multiply by -1 those rows I for which BI is less than 0, and add artificial variables as necessary to those rows, and then use your phase 1 problem. To obtain primal feasibility. Of course, once you've got your primal feasibility recovered, you know, of all the artificial variables are eliminated, become 0, and then you have a primal feasible basic solution to the original problem, and then from that point on, you just carry on with the regular simplex method, or phase 2, okay? Okay, so that's the basic strategy if the most complicated situation happens to arise. So let me see what example we have. I'm going to use the same example that you have in the book so you can follow it later, going through your book in more detail. I'll just go kind of quickly. Before I mention the example, let's just look at this optimal tableau. I'm assuming this is the optimum tableau with the original data, and then things will change. Okay, in this tableau we have R, which is WA minus C here. Then we have B inverse A. You've got B inverse B, which is B bar, and then you've got Z bar, which is CB B inverse B. Here, W is defined by the same basis, CV B inverse. All right. So, for example, if C changes, then the part of the tableau that is affected by that is this part, because C shows up only here. Okay? Then you will know what to do. If B changes, then B inverse B is affected by that. Of course, then you have to somehow take care of that, revise the right-hand side column, and then typically you may have to use dual simplex method because some component may turn negative here. If not, of course, things will be okay. Bless you. And for the third possibility, a column of AJ changes. Now, when you look at a column, a change in the A matrix, a single column, will affect this part, B inverse AJ will be different. It will also affect the reduced cost here, RJ, okay? But before worrying about the reduced cost, you need to worry about what's happening with the new version of the column. If this is a non-basic column, you don't have too much difficulty. No problem with that. So in that case, you just go with the analysis of RJ. In other words, just recompute RJ, reduce cost, and then do whatever you have to do. In other words, you either stop if RJ happens to be, for minimization, if it's less than or equal to 0. And if it's positive, you just enter the new variable. If, however, the column that has been changed is a basic column, a number of things can go wrong. The new version of the column, when you insert it in your old basis, in other words, when you revise that particular column of the basis, you may lose linear independency between the columns, okay? Because the new column may actually cause linear dependency among the columns of the B matrix, in which case you don't have a basis anymore. So you have to create a new one by introducing an artificial variable. So you throw out the basic column that used to be basic, which is no longer belongs into the basis. In place of it, you introduce a unit vector, which is the one associated with the artificial. All right, but the other possibility is the new version of the changed column, which is basic, may still maintain the linear independency among the columns in the basis, in which case you just have to revise the information in the tableau and then see how you go along with that. All right, so this is the main thing that you will, the main tool that you will be using, the optimum tableau with the appropriate revisions taking place. So let's see. Let's look at the example now. This is an example of the form AX equals B, X greater than or equals 0, where C is -2, 1, -1, 0, 0. 5 variables and 2 constraints, 2 functional constraints. The variables x4 and x5 are slack variables. You might want to take a note of that, okay? That's why they have coefficients of 0. So the original constraints were less than or equal to, so I just added 2 slack variables. After the addition of the slack variables, the constraint matrix looks like this one. So we did have a 1, 0 vector here, which was the x3's vector. But then when you add the slack x4 and x5, x4 has the same column. Okay? So that's a possibility, of course. And the right-hand side column is 6 and 4. This is the example also that's covered in the book. All right. The optimum tableau for this turns out to be the following. That's the optimum solution. So the optimal basis is defined by x1, x5 column. All right, so I'm going to look at the following changes. C1, which is minus 2 in the original problem. Let me just check something here. It could be +1, so let me just make sure that we have the correct data. Okay, yeah, it's minus. And we change it to 0. We also have a change in C2, which is currently 1. Change it to -3. That's the first change. Number 2. The B vector, 6, 4, is now going to be 3, 4. These are going to be independently handled changes, so we'll look at them separately. Number 3, A2. Let me just separate this case as ABC. In part A, A2, which is 1, 2, is going to be changed into A2 cap, which is -1, 5. Now, that's a non-basic column in the optimum solution, so this is the easy case. Okay? In part B, I'm going to take A1, which is a basic column, and it used to be 1, -1 in the original data. Now, we'll assume it is changed into 0, -1. This is a basic column, and it will turn out that the new matrix B cap, when you replace A1 with A1 cap, is no longer a basis. B cap is the version of B with A1 replaced by A1 cap. And then in part C, I'm going to take A1, the same A1, changed into A1 cap, which is this time 3, 6. This is again the basic case, but B cap is still a basis. Whether or not it's a feasible basis, we don't know. Nevertheless, it will turn. Of course, you need to also recognize when case B occurs or case C occurs, but I'll tell you about those. Okay? Number 4. Add a new activity, x6, which is not in the problem, with cost parameters 1 and column -1, 2. And finally, we add a new constraint, which happens to be -x1 plus 2x3 greater than or equal to 2. That's the new constraint. Okay. All right. So let's look at the first case, number 1. C1 is -2, C2 is 1. So the cost vector, which used to be -2, 1, -1, 0, 0, is now C1 is 0, C2 is -3. The other ones don't change, -1, 0, 0. So maybe I'm going to put them in different color because those are the ones that have changed. Okay? You should always keep the old data in mind, of course. So what do we do in this case? Simple. The part of the tableau that's affected by this is this part. That's the only part that's affected. Because C is here, CBB inverse, W is CBB inverse. The other parts of the tableau do not involve C. So for that reason, now, of course, you need to compute R cap, which is W cap A minus C cap. What is W cap? It's going to be CB cap if there's a change in the CB portion of the C vector times B inverse A minus C cap. This is how you handle this. So let's just do it. What is CB? C1 and C5. If you look at the basic variables are C1 and C5. So C1 in this case is 0. C5 also happens to be 0 by good luck. So things will be easier to compute. Times B inverse A. B inverse A is already in the tableau. How much is it? 1, 0, 1, 3. 1, 1, 1, 1. And 0, 1. That's your B inverse A. Minus C cap. 0, -3, -1, 0, 0. So when you compute this, of course, you just get minus the C vector, which is now 0, +3, +1, 0, 0. There's something wrong here. Okay, yeah, because this part is affected. Yeah, both of them turned out to be positive in this case. So you just put them in your tableau now. We may enter x2 now, which is non-basic. So all you have to do is revise the tableau and then do that. So the particular revision we need is the top row here, which is going to have 0, 3, 1, 0, 0 here. One, 1, 1, 0, 1, and what is that? 6, 10, 6, 10. Yeah. Also, the right-hand side value is also changed. Well, how much is it now?
0.
Okay, thank you. CB, B inverse B. You just compute it, okay? Okay, so here, of course, you just use the regular simplex method. You enter that one, and you look at the ratios. This one exits. You pivot on that, and then you get the new solution, maybe in the next iteration or perhaps later. I don't know. Okay. Number 2. The change in B, 6, 4. So B cap is now, what is it? 3, 4. In this case, of course, the part of the tableau that's affected is this part. B inverse, B is no longer B, but it's B cap. So what you have here is no longer Z bar, but Z bar cap, which is, what is this? CB, B inverse, B cap. Okay? You need to compute that, but the more important part is here, of course. So let's just compute B inverse times B cap. B inverse is already available in the tableau. Since you started out with X4 and X5, which used to house the identity matrix in the initial tableau, then B inverse times the original A matrix will make a copy of itself where the identity was at the very beginning. Okay? So this is your B inverse here. 1, 1, 0, 1 times B cap, 3, 4. How much is that? 3 plus, well, 3. 3 plus, that's 7. This is already greater than or equal to 0, so primal feasibility is okay. Dual feasibility is already okay because we're looking at the changes independently. Okay. Dual feasibility is also fine. So this is also optimal. Optimal, the basis is optimal. The solution is different, of course. What is the new solution? So basis is optimal. The new solution is XB is equal to 3, 7, or X1, X5 equals 3, 7. Other variables are 0, X2, X3, X4. They are numbers again, 0. And the objective value is now, how much? Well, CB, what is CB? CB is -2 and 0, okay. Times this 3, 7, which gives you -6. Yes, it is -6 now, okay? Number 3. A2 cap is -1 and 5. This is a non-basic column, so things will not be too difficult. You need to compute R2. Well, the column associated with X2 in the optimum tableau is affected by this. So you need to revise. To revise that, you compute R2 first, which is the old W times A2 cap minus C2. How much is W? -2, 0. How did I know that? Well, again, X4, X5 are the initial slack or initial basic variables. And for that reason, since they had zeros in the original cost vector, -2 and 0 gives you the W. Okay. Times minus 1, 5. That's a cap. Okay. Minus 1 and 5. Minus C2. How much is C2? 1. So how much is this? That's 2 minus 1, which is 1. So I know that I'm going to enter x2. And I need to compute also the y2 vector, which is B inverse times A2 cap, again 1, 1, 0, 1, from the old tableau, times minus 1, 5, which gives you minus 1 here, and minus 1 plus 5, so that's 4, okay? Gives you that. So, now, x2 column has a 1 here. It's changed. It has minus 1 and 4 here. The rest of the stuff did not change. So I'm not going to write them down, but all the black numbers in the optimum tableau, they are still here. Okay? And of course, this one exits. So you pivot on that and you get the new solution. Okay. Part B. A1 cap is 0 minus 1. That's a basic column. If you're not following something, please raise your hand and ask, because I see some puzzled looks in some of your faces. You know, I know that look. I know that look. You know, if things don't really, you know, fit, I know that. You keep writing, but you don't really follow. So, is everybody following?
Somebody blind.
Somebody blind, huh? What do you mean blind?
Blind.
Oh, okay. All right. In the basic case, the current basis is the columns of x1 and x5. x1 has a column of 1 and minus 1. x5 has a column of 0 and 1. This is a valid basis, of course. That's the old optimum basis. Now, B cap retains x5 column, but the x1 column is different now. So x5 is 0, 1, but x1 column is 0, minus 1. And you can just immediately see by inspection that there's linear dependency. One is the negative of the other one. Of course, things could be much larger, in which case you may not be able to see it. So I'm going to tell you what to do if this sort of a situation arises. So the easy way to, well, the way to define this is the following. Compute. So let me write the general way of handling this situation. In general, if AJ is changed into AJ cap, and assuming that J refers to a basic variable, what you do is you compute YJ cap, which is the old inverse times AJ cap. The old inverse times AJ cap. Okay? So this will output YJ vector, which is going to have Y1J, Ykj up to Ymj. Okay? And assume Aj is the kth basic column in B. So you've got Aj, but it's in the kth position in the B matrix. Okay? That's why I isolated Ykj here. If Ykj happens to be 0, then B cap, which is obtained from B by replacing the old Aj with the new Aj cap, is not a basis. If, on the other hand, Ykj is non-zero, then B cap is a basis. Okay, why? You need to know why. And the reason is the following. We've got Yj cap defined by B inverse times Aj cap. This is, of course, the same thing as B multiplying Yj and obtaining Aj cap. If you pre-multiply both sides by B, that's what you get. Okay? Now, B is a bunch of columns. It's got, say, m columns in it. So what this does is, if you look at this, it takes the first basic column, AB1, and the ABK, the kth basic column, and then the last basic column, say ABM, multiplies these things by Y1J cap. I should put cap here, sorry. Why don't you put your caps here? Yeah. Because that's the way I defined it. Okay? So Y1J up to Y1K cap, and then Ym K cap. And you get, what do you get? You get Aj cap. A1 J cap up to Am J cap. This is already given to you. Okay? This is computed. So it's computed and available. These are also available. By the way, this particular column is equal to Aj, the old Aj. Okay? So, when you look at that, this simply tells you that you take the first column, say AB1, let me just write AB1 in it, times Y1J cap, plus so on and so forth. You take the kth column, which is your Aj, this is the kth column, times Ykj cap. I'm just multiplying these two. Then last column, times Ymj cap, and you set it equal to a J cap column. Okay? So this is the matrix, or this is the, we're looking at everything in the column space like this. So you're asking yourself, can I swap? There's something wrong here. There's no cap here. Sorry. There's no cap in this one. That's the original column. Okay? So you're asking yourself, can I swap these? In other words, can I simply remove aj from the old basis and put the new vector in? And can I still maintain linear independence? And there's a theorem in linear algebra, which you may remember from your old linear algebra days. I'm not sure if how well you remember, but it says, yes, this replacement is okay. In other words, the new matrix at the end of the replacement will be a valid basis if and only if, what is true, if and only if this multiplier here is non-zero. This is one of the actually homework questions, end of chapter questions in probably chapter 2. Okay, you're asked to prove that. That's a theorem. So, answer is yes. If and only if, well, can I swap and still maintain a linear independence? The answer is yes, if the multiplier for that one is different from 0. Okay? So these are the multipliers which expresses the incoming or the new candidate in terms of the old basic columns. And whenever the multiplier in that expression happens to be non-zero, the replacement is okay. Of course, the replacement is always okay, but the replacement will be okay, and also the new basis or the new matrix will be a valid basis only under that condition. And whenever that condition fails, of course, the new one is not a basis. So in this case, we compute back to our example. Okay? So you compute y1 cap, which is the old inverse times a1 cap. The old inverse is 1101, as far as I remember. Yes. Times a1 cap 0 minus 1. It gives you 0 and minus 1. It just makes a copy of itself. It's just by coincidence. Okay. What is j here? It's 1. What is k here? It also happens to be 1, because in the optimum tableau, x1 is listed first, x5 is listed second. Okay? Or here, you can see that a1 is the first basic column. So they are both 1 in this case. So I'm looking at y11, and the question is it non-zero or not? It is 0. Okay? This is the value you're looking at. Okay? So that is equal to 0. So b cap is not a basis. After all that explanation, now you need to go ahead and, compute the new solution. So how do we do that? It's really not too difficult. We just look at the old tableau. Except that I leave some space here for a particular reason. Z, x1, x5. So we've got the old numbers. By the way, x1 column is changed, so minus 3, 1, 3, minus 1, 1, 1, minus 2, 1, 1. What else do we have? x4, 0, 0, 1. The right-hand side, minus 12, 6, and 10. Now this part is different now. We have 0 and minus 1. That's y1 cap. How much is this guy? You need to compute also that one. R1 cap is 20, sorry, minus 20 times A1 cap. Let's just write it this way. CB, B inverse A1 cap minus C1. Okay? So when you compute that, what you get is 0. I have 0. You could just plug in the numbers and that's what you should get. So I have a 0 here. All right. Pardon? Is it something else? Is that what you're saying? I don't know. Let's compute. CB is minus 2 and 0. B inverse A cap is how much? Where am I? This one. 0. Yeah, B inverse A1 cap is 0 minus 1. Minus C1. C1 is how much? Minus 2. So I've got, you're right. You've got 2. Yeah, we have 2, sorry. So this is 2 actually. Okay. Now, this is not in proper form yet. Well, actually, what you want to do is you want to have a x1 column, you want to have a 1 here, 0 here, 0 here, but you cannot pivot on this guy. Actually, you know, that's the other way of seeing this. And since you cannot pivot, you cannot create the unit vector here. 0, 1, 0 cannot be made. Okay? So what do? You introduce a new variable, which is an artificial variable. And it has, of course, what does it have? It has 1 here, 0 here. And then you forget, you turn this into a phase 1 problem. So all of this is gone. You just throw them away. And then you have a 1 here, minus 1 actually. Of course, this one also changes. So the phase 1 problem will minimize the artificial variable, the sum of the artificial variables. In this case, there's only 1. You will minimize x6 subject to the constraints that you see in the tableau. Okay? And of course, first you need to also get rid of that guy, which means you add 1 times this row. So you get 0 here, 0. This one becomes 1. This one becomes 1. That one becomes 1. This doesn't change. And this one becomes 6. So that's the initiating tableau for phase 1. Maybe I'm going a little bit fast, but you know, I don't want to lose too much time with these things. It's just mechanical stuff, you know. I mean, you are so well exposed to linear programming now, you can do all of this quickly. Okay? All right, so the phase 1 problem, solve this, and then once you solve it, if the artificial variable becomes 0, of course, you have a basic feasible solution to the original problem, from which point on you can carry on. All right, let's take a 10-minute break, and then we'll just look at the other remaining stuff in the second hour.